All right, so now we're going to focus on linking up, looking at the relationship between a confidence interval and a hypothesis test. And we're going to look at this relationship with the confidence interval and hypothesis test we have learned so far, and that is making inference for a population mean mu. Now, this concept might be a little bit more difficult to wrap your mind around, so we're going to draw a picture to make it a little bit easier to visualize. So we're going to draw a picture of the hypothesis test and shading in p-value areas and such that corresponds to the alternative hypothesis of not equal to. All right, so remember we said when we have a not equal to alternative hypothesis, we're going to shade in the area above the positive version of the test statistic and below the negative version of the test statistic to get our p-value area. All right, and we're going to draw a couple of other things too. So let's go ahead and draw the t-distribution for the situation where our alternative hypothesis is not equal to and we reject the null hypothesis. So we have some t-distribution. These are centered at 0, unimodal and symmetric. And if we reject the null hypothesis, then what is true? What is true about the p-value and the alpha? If the p is low, the null must go. So, if we reject the null hypothesis, that means that our p-value was less than or equal to alpha, right? So let's go ahead and draw in the alpha region and the p-value region. First, let's draw in the p-value region. So the p-value region is going to be the area to the right of the positive version of the test statistic plus the area to the left of the negative version of the test statistic. So that's our p-value. Now, if we reject the null hypothesis, that means that our p-value was less than or equal to our alpha level. Now, it turns out when we think about hypothesis testing in terms of our alpha level, just like we started off with when we did a confidence interval, we're going to put half the alpha in the upper tail and half the alpha in the lower tail. Now, if the p-value is less than or equal to the alpha, we're going to imagine that it was less than. That means the alpha region was bigger than the p-value region. So that means that our upper alpha critical point and the negative version of it are somewhere in here. They did not fall in here because then the alpha would have been smaller than the p-value region. All right. So we've drawn that picture. Now let's draw the picture of the hypothesis test with the not equal to alternative hypothesis where we fail to reject. Now if the p is low, the null must go. If we fail to reject, that means that the p-value was bigger than the alpha. The p wasn't low enough. So we're going to draw a picture of that. In this case, the p-value, since we have a not equal to alternative hypothesis, is still going to be the area to the left of the negative version of the test statistic and the area to the right plus the area to the right of the positive version of the test statistic. But this time, the p-value region, I should have drawn that a little bit bigger. That was not good planning. This time the p-value region is bigger than the alpha region. So we're going to draw our p-value region the way it should be, that it's the area to the right of the positive version of the test statistic plus the area to the left of the negative version of the test statistic. So I made it a little bit bigger this time so we'd have room to draw our alpha. So the p is bigger than the alpha because we are in the fail to reject scenario. So a half of the alpha is going to go in the upper tail and a half of the alpha is going to go in the lower tail. All right, so we've got our picture of the reject and the fail to reject scenario. Let's take a look at the fail to reject scenario. when we fail to reject, it doesn't matter whether that original test statistic was negative or positive. It is somewhere between negative t of alpha divided by 2 and positive t of alpha divided by 2. So we have the following inequality when we fail to reject. We have that negative t of alpha divided by 2 is less than your test statistic, which is less than the positive t of alpha divided by 2. And what's our test statistic? Well, that is x bar minus mu naught over s divided by the square root of n less than t of alpha divided by 2. Now, that inequality, this inequality should look familiar. That is the one that was inside of our probability statement when we created our confidence interval. Remember, we had an inequality that looked just like that, and we got mu by itself in the center. We used algebra to get mu by itself. So that means that we can draw a certain conclusion. So first, we'll write down the context that we saw this inequality. We had that probability statement when we created our first confidence interval, that negative t of alpha divided by 2 less than mu over s divided by the square root of n less than positive t of alpha divided by 2 equals 1 minus alpha. And that was for our 1 minus alpha percent confidence interval. All right. So what we can gather from this is that the events that lead to the decision to fail to reject the null hypothesis for the two-sided hypothesis test are exactly the same events that form the 1 minus alpha percent confidence interval for mu. So what's the moral to the story? If your confidence interval contains your null hypothesized belief of what the true mean is, then we automatically know that we would fail to reject the null hypothesis for the two-sided test. That is, the null hypothesis mu is equal to mu naught against the alternative that mu is not equal to mu naught, and vice versa. So for instance, if I have a confidence interval for the true mean weight of a 6th grader, and let's just say it goes from 95 up to 105. Totally made up example. All right. So my confidence interval, my range of values where I think my population parameter lies for 95% confidence is 95 to 105. Now, if I would want to use that same data set and ask to do a test for the null hypothesis that mu equals 100 against the alternative that mu does not equal 100, that's the two-sided test at the 5% significance level, and this is a 95% confidence interval, then I already know that 100 is in this range of values. 100 is between 95 and 105. It is a possible value for my parameter mu. So my null hypothesis that mu equals 100 might actually be true, according to my confidence interval. So I already know that my p-value is going to lead to the conclusion to fail to reject the null hypothesis. So that is the moral to the story that we are discussing in this set of lecture notes. We are going to have an actual example of this in our next set of lecture notes when we do some examples.